Hi everyone. In this lecture, we are going to introduce atoms and begin to talk about starlight. So by the end of this class, we'll go over why atoms emit and absorb light and how, looking at the type and the color of light that's emitted, as well as looking at the difference between thermal energy and temperature, and then learning about blackbody curves, being able to relate peak wavelength to color and temperature using what you'll learn to be Stefan-Boltzmann's law and Wien's law. So to start, light. Everything that we know about space comes from light. So you remember that light is electromagnetic radiation in the form of waves, and the visible spectrum is what we can see with our eye. Very short wavelengths, small wavelengths are very high energy. Long wavelengths are very low energy. So let's take a step back to the most introductory chemistry that we're going to go over and think about atoms. So everything is made up of atoms, and atoms are made up of a nucleus. So a nucleus is in the center of the atom, and the nucleus is made up of protons, which in this diagram are blue. They are positively charged, neutrons that have a neutral charge, and then there's electrons that go around the nucleus. So the nucleus is made up of protons and neutrons, a positive charge and a neutral charge, meaning that the nucleus is going to have a positive charge. The electrons are the negative charge. So the electrons are in what we call the cloud, circling around the nucleus. The electrons have a negative charge. So the electrons are attracted to the positive charge of the nucleus. So when we have a neutral atom, it means that the overall charge is balanced. So there's 3 protons, there's 3 electrons. So that means there's positive 3 and negative 3, so it is balanced. It is a neutral atom. The overall charge is 0, neither positive nor negative. So one thing to note about atoms is most of the mass of an atom is actually in the nucleus. And the nucleus is teeny tiny compared to the whole atom. Most of an atom is just empty space. So if this is the size of an electron cloud, if we scale it to the size of a football field, so here's, let's say we're scaling this to the size of a football field. So this is how a football field would fit within our atom if the nucleus was a grape seed. So imagine a grape seed in the middle of a football field. The nucleus is almost all of the mass. That grape seed is almost all of the mass of the whole atom, and it is teeny tiny in comparison to how large that atom is. Now, atoms are also teeny tiny, so we have to think about scale when we're talking about this. So think of an electron being, think of the atom being the football field and all the parking lots surrounding it. And the nucleus, where all of the mass is held, is a grape seed in the middle of the football field. So this is the periodic table of elements, which I hope looks at least a little bit familiar to everyone. Chemical elements are set by the number of protons in the atom. So the number of protons is going to determine which element is which. So if there's an atom that has 1 proton, it is a hydrogen. If there is an atom that has 27 protons, it is cobalt. So this is always constant. Any atom with 27 protons is cobalt. Any atom with 5 protons is boron. However, the number of the neutrons and the electrons in the atom can vary within the same element, but the number of protons are always set. The number of protons determines which element we're looking at. So, 2 atoms can actually bond together. This is usually due to a collision. They collide into each other, and when they're bonded, it means that their electron clouds are a little intertwined and they're sharing electrons between the 2 atoms. So when you have bonded atoms, when you have 2 or more, it can be 2, 3, 4, that forms a molecule. So a molecule is made up of multiple atoms that are bonded together. So they're sharing some electrons. So within stars, atoms very rarely bond together. Molecules are super rare in stars. We really only see molecules forming in planets' atmospheres. The collisions on stars are way too violent and the temperatures are incredibly high. So we don't actually see the formation of molecules in stars. We do, however, see them on the on the planet's atmospheres. So example, in our atmosphere, we have H2O, water. We have CO2. That is, it would be CO2, that's 1 carbon, and 2 oxygen. H2O is 2 hydrogen, 1 oxygen. So those atoms are able to collide and bond together, creating molecules. Really only in atmospheres. So when we think about that, those electrons moving around, we think about the fact that the electrons are orbiting around that nucleus. So they're attracted, the electrons, remember they're negatively charged, they're attracted to the positively charged nucleus because they're attracted to those positively charged protons. So this keeps them bound to the nucleus, keeps them rotating close to the nucleus. So it actually takes energy to break this attraction. It takes energy to break an electron away from the nucleus. So the atom has this binding energy, and it depends on the size of the orbit of the electron around that atom. So which do you think would be the highest energy level? Where would be the highest energy? Close to the nucleus? Anywhere in the electron cloud, or very far from the nucleus? Which location would have the highest amount of energy? If you had to guess. So if there's the highest amount of energy binding an electron to the nucleus, you would think that that electron has to be close to the nucleus, which is right. So the closer the electron is being held to the nucleus, the higher the energy level is keeping that electron there. So that binding energy is going to be high. So these closely orbiting electrons, if they're closer to the nucleus, that means there's a stronger attraction. There's a stronger force keeping them there, meaning it's going to be harder to remove. And it will require more energy to break that electron away because that attraction is so strong. Now, atoms have very specific sizes of orbits, and there's a specific amount of energy per atom for this binding. So electrons are orbiting along these specific orbits. They're sometimes called the permitted orbits in terms of how far away from the nucleus can the electrons be. And we think of these permitted orbits, these specific orbits, as levels of energy or energy levels. So the closest orbit to the electron is going to be the highest energy. As we move away, the closest level of orbit towards the nucleus, I misspoke, is going to be the highest level of energy. As we move away from the nucleus, it's going to be lower energy levels. So here's an example of what I mean by that. If this black dot is the nucleus, the first level, the first permitted energy level would be, this is just a diagram, of course, and then we have the second level, and then we have the third level, and then the fourth level. So the highest energy level is going to be the first level because it's being held very close to the nucleus. So there's a huge attraction there. There's a really strong force. There's a lot less energy being put into holding an electron that's on this fourth orbit because it's much further away. So when an atom's ground state is the lowest energy level, the smallest orbit. So the energy level that's closest to the atom. Now, when an atom gets excited, it moves up in energy levels in terms of it moves outwards, away from the nucleus. So it could move from 1 to 2. It could move from 2 to 4 when an electron gets excited. Now, how do you pump up an electron? There's really two ways. You have to apply energy to this atom to get one of the electrons to be excited. So this can either happen through a collision, or it can happen by the atom absorbing a photon of light. So absorbing this particle of light, the atom's going to get super psyched, and one of its electrons will be able to jump from, let's say, ground level, level 1, all the way up to level 4. So that's going to be a big jump in energy. So photons, I'm talking about photons here. So photons of light are a group of EM wave, the electromagnetic waves that have a specific set of energy. So the photon must be the right wavelength to excite an electron. So atoms aren't excited by any wavelength. It has to be specific to that atom. So the atom is only going to absorb a certain set of wavelengths. So only that certain set of wavelengths will be able to be absorbed and excite that atom. They don't stay excited for very long. So here's a diagram. So here is our atom, and here is a short wavelength in the purple, the violet. Not the right one. The atom says, no thanks. That's not, I can't absorb that one, don't want it. Here comes a blue photon. The atom says, awesome, definitely absorbing that one. So the atom is going to absorb this photon, and its electron, the little black dot, is going to jump up in an energy state. So it's going to jump away from the nucleus out towards a different level of energy. Yeehaw, he says. And then it's gonna be done. So the electron jumps up to its level, and it jumps right back down. So as the electron jumps back down to its initial state, it's going to emit a photon. So it's going to emit the photon right back out. So the atom's going to get excited by a photon. The electron will jump out to another orbit, and then it will fall back down. It will drop back down, and the atom will emit a photon back out. So each atom has a really unique set of these energy levels, and each atom is only going to absorb and emit photons at a very specific set of wavelengths. So that is where in the first diagram here, this was not the right wavelength for this atom, so it would not absorb it. So we're actually able to identify the elements by studying the wavelengths that are being absorbed and emitted. So we can actually use, if we excite an atom, we can use the information about which wavelengths will excite that atom to determine what the atom is, to determine what element we're looking at. So if we look at this diagram here we have, this is electromagnetic radiation. We've seen this diagram before. We have our visible spectrum. We have radio, infrared, visible, UV, X-ray, and gamma rays. So which of these would have the highest wavelength? So the highest wavelength, the largest wavelength would be our radio waves. This is just a review slide here. What about the highest total energy? The highest total energy is inversely proportional to our wavelength. So we know that the shortest wavelengths are going to have the highest energy. The shortest wavelengths are also going to have the highest frequency. So in terms of visible, so which color that we can see with our eyes, our highest wavelength is going to be red, but the highest total energy is going to be purple and blue. So the highest energy that we can see of a wave is going to be the blue and the violet. The red is going to be lower energy. So what color will be emitted when an electron close to the nucleus is very excited? That would be, remember that the electrons closest to the nucleus are being held in by a really strong force because they're very close to the nucleus. So it's going to take a lot of energy to break that attraction. It's going to take a lot of energy to excite the electrons that are closest to the nucleus. So in this case, we would expect a photon of blue or purple light to have a high amount of energy, high enough to excite an electron that's very close to the nucleus, because we know that takes more energy than exciting an electron that's on the outskirts. So let's think of an example, and an example being the element called neon. So neon atoms can be excited when they are in a tube. So you can put some neon atoms into a glass tube, like this person did here, and excite them by pumping electricity through the tube. So what you're going to get is this orangey red glow, because as the current flows through the gas, it's colliding, you're exciting the electrons, so the atoms are constantly jumping up, falling back, jumping up, falling back, jumping up, falling back. So you are constantly emitting these photons in the specific wavelength that neon emits. So neon, if you see a neon sign, it is always going to be a red or orange. So you always see this red-orange color when you see excited neon. That's telling you it's literally neon in these tubes that's getting excited by the electricity and emitting photons in the neon's preferred wavelengths. But if you think about other neon signs that you might have seen, is they're not always this color. Sometimes they're blue, sometimes they're red, sometimes they're green. Sometimes you see a specific company's logo made of one of these neon lights. So the trick is, we call them neon lights, but they're not actually neon. So if you see other colors, it's just that they've used a different gas than neon. So they've found, so this one's probably hydrogen because it's pink. They've found the gas that will emit photons within the visible light at the wavelength of the color that they want. So here is an orangey red, here is a pink. So if you wanted something, you wanted a neon, in quotes, a neon light that was blue, you would need to find a gas that will emit photons in the blue wavelength so that you can have a blue planet here, or a blue whatever sign you're trying to make. So they're not actually all neon lights. They're all different kinds of gases being excited. The color depends on which gas you put inside. So here is a picture, for example, of some stars in space, and you'll notice they're not all the same color. So there's some that look more red, some that look more yellow, some that look more white, some that look blue. And this is because we are seeing the visible wavelength that they're putting out. So we are seeing these stars in the visible wavelengths because that is all that we can see with our eyes. So let's get into what that means a little bit. So radiation, when we're talking about stars, really this color of a star is indicative of its temperature. So the color of a star can tell us a lot about the temperature of that star. So starlight, the light that we see from a star, is from the gases that make up the surface of the star. So the photosphere is the surface of the star. So the outermost layer of the star. We're going to get into these terminology more about the inner workings of stars in the middle of this class. So you don't have to worry about that yet. Just remember that the photosphere is the outermost layer, and it is dense enough that it emits light so we can see the light, but it's transparent enough that the light actually does escape. So it doesn't keep all the light. It escapes to the point where we can see it. So we aren't actually seeing anything about the core of a star when we're looking at it. We're just seeing the gases on the surface of the star. So stars are creating light because they're very, very hot. And that light is produced by the fact that all of the particles in the photosphere are accelerating. So that's the acceleration of all of these charged particles in the photosphere. It's going to cause motion, it's going to cause change of motion, and it's going to cause changes in the electric field of the electrons and the emitted electromagnetic radiation. So stars have a lot of excited atoms on them. So the atoms and the molecules on our stars, if there are molecules, they are constantly in motion. Now, the hotter the star, the more agitated the particles are. So when we talk about thermal energy, it's different from heat and temperature. Thermal energy is the state of agitation of the particles of the object. Let's say it's a star. Now, the flow of that thermal energy is what we call heat. And the speed of those particles, the speed of that flow, is what we measure in temperature. So they are related, but they're all different. So the temperature of a star, when we talk about the temperature of the star, we're only talking about the temperature of the gases in the photosphere, so in that outer shell, the surface of the star, because that's all that we can see. And when we talk about temperature, we report it in the Kelvin scale. So the Kelvin scale is similar to Celsius, it's just offset by 270 degrees. So 0 Kelvin is what we call absolute zero. This is where an object has absolutely zero thermal energy. There is no thermal energy. This is at 0 Kelvin. So this is equivalent to negative 273 degrees Celsius or negative 460 degrees Fahrenheit, where there is no thermal energy in that object, nothing. And then things warm up from there. So absolute zero on the Kelvin scale is negative 273 Celsius. Now, the cool thing about the Kelvin and the Celsius scale is the scaling is the same, it's just offset. So a change in 1 degree Kelvin is the same as a change in 1 degree Celsius. So if 0 Kelvin is equal to negative 273 Celsius, then 1 Kelvin is equal to negative 272 Celsius. So the scaling's the same. The change in 1 degree is the same. It's just offset by 273 degrees. So just a side note, because you will start to see Kelvin quite a bit when we start talking about the temperature of stars. So everything that is above 0 degrees Kelvin is emitting radiation, is emitting light in some wavelength. So the way that we think about stars emitting light is that we assume that they are what we call black body objects. So black body radiation is the model of an object that absorbs and emits, so re-emits, all of the radiation that falls on it. So it's always in equilibrium. So it's absorbing and re-emitting all the time. All of the light that falls on it is absorbed and re-emitted. So stars and planets are not actually perfect black bodies in real life, but we assume that they are. So it's used sort of as a first approximation. We assume that stars and planets are these perfect black bodies in order to be able to understand what's going on and make connections. So, for example, I'm trying to simplify it here by assuming that object A, some object that we're looking at in space, assuming it absorbs and re-emits all of its radiation, all the radiation that falls on it, we can look at, well, what wavelengths does it absorb and emit, and how much at each of those wavelengths. We can then graph this to determine what we call the black body curve or the graph of wavelengths absorbed and emitted by this object. So here is an example of radiation emitted by 3 different objects. So we have the purple line, the red line, and the green line. So the hotter an object, the more blackbody radiation it will emit. So when we see these blackbody curves, we're always looking at wavelength along the x-axis, and then the radiation density in terms of how much radiation on the y. So here we see the purple curve is hotter at 5,000 Kelvin, and it also is emitting more radiation. You see that this is much higher than, say, the radiation emitted by the green line, which is much lower. So blackbody radiation is made up of photons with specific distribution of wavelengths, and electrons have different speeds and energies, as we've talked about. So the wavelength of maximum intensity is what we call the peak wavelength. So it's the wavelength that the object emits the most radiation. So if we look at this blue star, for example, literally the blue star, and the blue curve, we see that the peak in radiation, the peak wavelength, meaning the wavelength that is emitted the most, the highest on the curve, it's at about 400 nanometers in wavelength, which is in the visible at a color of blue. So this star is going to look blue to us. If we look at the yellow curve, the yellow curve's peak, meaning the wavelength that it has the highest intensity, is more in the yellow wavelengths. So this star is going to appear yellow. Now the red star, I have a star here at the peak, which is at about 700 nanometers. So this star is going to look red because 700 nanometers is in the red. So notice that this blue star is emitting wavelengths lower than blue and higher than blue. So we look under the curve here of the blue. It's emitting all of these wavelengths, but the highest, the wavelength that is emitting the most, is in the blue visible light. So it's going to appear blue to us because it's emitting more blue than it is emitting any other wavelength. So here's another example of an object at 7,000 Kelvin, an object at 6,000 Kelvin, and an object at 5,000 Kelvin, and their respective blackbody curves. Excuse me. So the peak wavelength, you'll notice it's always somewhere in the middle of all of the total wavelengths that are emitted. It's never over on the edge because these curves are always bell-shaped. So they're always a bell-shaped curve. And you'll notice that the hotter objects have more total energy. So there's a larger area under this curve. There's more total energy being emitted here from this object at 7,000 Kelvin than there is from this object at 5,000 Kelvin. So this is essentially what we call the Stefan-Boltzmann law. Now there's another law called Wien's law that relates the temperature to the color. So as I was explaining a couple slides ago, the peak wavelength color, if it's in the visible light, is going to be the color that we see, literally the color that we see. So the wavelength, the peak wavelength, depends on temperature. So the hotter the object, the shorter the wavelength. So the hotter objects are going to be blue, the cooler objects are going to be red. Little counterintuitive because we normally see red as a hot color and blue as a cool color. But when we're talking about stars, blue has a shorter wavelength. Blue is going to be a hotter star than a red star. This is what we call Wien's law. So here they are written out. Wien's law, we have the wavelength related to the temperature. So I should say the peak wavelength. So that's why it's gamma max for the peak wavelength. And as the peak wavelength goes up, the temperature goes down. As the temperature goes up, the peak wavelength goes down. Stefan-Boltzmann's law relates the temperature to the total energy that's radiated. So as the energy goes up, the temperature goes up. The temperature actually goes up to the power of 4. So as the energy goes up, the temperature goes way, way, way up. So these are some common laws, common understanding that we have about these black bodies, about really anything emitting the EM radiation in space. So here's another example where we have a blue star. Its peak radiation is in the bluish purple, and it is about 7,000 degrees. It has it is emitting a higher total amount of energy than these less hot stars. So the coolest star shown here is 4,000 Kelvin. It's going to be a red star because you'll see its peak is more in the red, and it is emitting much less total energy than the other two stars. So the total energy is equivalent to the total amount of energy that is released, the total amount of area underneath the curve of the black body, underneath the black body curve for that star.